Section 3.4, related rates. We have a procedure here, and it's very important that we try to remember what the procedure is when we are trying to find a rate of change with respect to time. We will be using implicit differentiation, so hopefully you've covered that first section and you've taken a look at the freestyle, because I really go into implicit differentiation in depth there. Not only will we need to draw the figure where we can and choose variables for anything that we don't know, we'll also need to write down what is given so that we can keep very close track of all of the unknowns, okay? Don't forget to use your DDT. So whenever we are doing stuff with respect to time, you will always know what the variable that you're taking derivative with respect to should be, okay? And I know that we're introducing this DDT, but like I said, I cover that in the freestyle. So writing an equation relating the variables, if we are noticing that something will be changing, we use a variable letter. But if we have a quantity that is constant, let's use a number and look for secondary relationships between quantities to reduce the number of variables. This one will be super important. You need to do it almost every time, okay? And it's essential for you because you don't want to take the derivative of something that doesn't need to have a derivative be taken. All right, implicitly differentiate both sides with respect to t is where we're actually going to start with this very first problem, okay? And I know I'm skipping the geometry formulas. We'll be using them as we move through lecture. Okay, so I'll come back to that in a minute. Examples in this problem, little typo there. The first three steps of the procedure are done. We need to complete only the last two steps. Well, what do you mean the first three steps are done? Well, first of all, it says choose variables, and we already can see that there's going to be a y and there's going to be an x because this is the equation. So this is a mathematical equation, and what kind of thing might give me an x times a y equation? Well, when imagine geometry, hopefully you notice we were using geometry formulas. Which formula will you have something times something? There it is right there, the rectangle, okay? So something times something. Now in the formula that you're given, it says L times W, length times width. But if this rectangle was on the coordinate plane, you would naturally do X times Y, right? So imagine that I have a coordinate plane and I go out to X and I go up to Y, and then I want to know the area of this rectangle. And by the way, basically everything that's important in calculus second semester will be about finding areas on a coordinate plane. So this is a great place for us to start, okay? We need to complete only the last two steps means that we've been given this formula. That's step two. We need to write an equation. Hey, that equation's already been written for us. And it looks to me like x and y are both variables. We don't know, how the area is going to shape up. So we have these two unknowns, and there aren't any constants other than that we know that the area when we're done will be a 12, right? And so the next step, step 4, is to literally do implicit differentiation. And it feels different because I'm using that DDT, okay? So I just want to show what that looks like, and I'm basically going to say here in x times y, I want to do the derivative with respect to time. So this is step 4. I am applying a derivative to both of these things. Now remember, the derivative of x is going to be 1, and I write down a dx dt. And then I also have, okay, so when I start taking the derivative of this, remember how I think of this as a product? Then I really have x times y, and I need to use the product rule. So the product rule says I should have something times something plus something times something. And by the way, I'm going to go ahead and say that the derivative of 12 is 0. So I know I'm going to get a 0 over there. And what are my two somethings? Well, remember, if I take the derivative of x, I will get a 1, and that will be a dx dt. And then if I take the derivative of y, I will get a 1, and I will have a dy dt. And so I should multiply this times this, and that times that. Ooh, those arrows look terrible. This times this, and that times that. And so I'm going to write down then, inside of here, I have the x times the dy dt. and I have the y times the dx dt. And ooh, my handwriting has suffered over the break. Okay, so what do I do next? Well, it turns out each one of these things is either a variable like that has a constant value that I can find. For example, dx dt has been given to me. I now know that that is -6. So I'm going to substitute that in. I also know that y equals 4, and so wow, this piece will disappear as well and just turn into a plain old constant. And let me write those constants down. So this is my 4, and this is my -6. What about x? It doesn't look like I've been given anything about x, and it also doesn't look like I've been given anything about y. But here's the thing. I think technically, let's go back up here. I think technically not all 3 steps have been done here. I put a star on something, and you definitely should put a star on something, and you might want to even highlight it too if you've got a highlighter. I think that this is actually it's so important, it should actually be its own step. So let's call 3C its own step and make sure that you always do it. Look for secondary relationships between quantities to reduce the number of variables. I don't want there to be 2 unknowns. In fact, what I specifically want to do is find, ready? Find dy dt. How do I know that I want to find dy dt? Well, it turns out it was given to me as part of the question. And you'll see it in, this next one is a word problem, right? I mean, we have a whole paragraph. So inside of that paragraph, we will have to look for what is the thing that we need to find. In this one, we just needed to find it on the page. Dy dt is the thing that I need to know. That's the thing that I need to solve for. So here it will be dy dt. Now what about x then? Well, it turns out x is something that I can find. For example, what if I know that y was 4? Didn't I know that? Right here, it says that y is 4. So can't I plug that 4 in right there? And won't I get, by the way, so this is step 3C. If I say that x is something that I don't know, but y is a 4, then x times 4 equals 12 is a very easy thing to solve for. So x equals 3. And that means right here, I can put in, ready, that 3. And here's my plus sign, and here this equals 0. And now you're like, ooh, I have no idea what we're doing. Trust me, we just need to practice these a bunch of times. So you'll get familiar with it as we move through it. Right now, let me rewrite it without, so much calculus in it, so many parentheses, so many colors. Why don't I just do this? 3 dy dt plus 4 times -6 is actually a -24, and that equals 0. I'm going to add 24 to both sides. I'm going to get 3 dy dt, and that equals 24. I'm going to divide by 3, and I'm going to say then my final answer, dy dt, whoa, handwriting, dy dt equals 24 divided by 3 is 8. Okay, so you'll notice that I'm on number 3. I don't want to do those first ones first. I actually want to do one that I think is easier in some senses because a couple of our steps are not present. We don't have to worry about them. So to start on the first part, it says draw a figure if necessary and choose variables for all of our unknowns. I'm going to tell you that in here, the more I do this, the more I wish that the very first step said read the problem 3 times. Literally. Just trying to understand this particular problem, it took me 3 times. I was doing it in class and asking students to read it. I asked 3 students to read it. That way I could really make sense of it. So pause if you haven't read it and read it now. And if you've read it once and you realize you don't get it, read it again. Okay? I'm going to start trying to draw it now. So I've got my policeman. There's my policeman wearing his policeman cap. And he's traveling towards this intersection. There's an intersection. And he spots a car. And it's driving away. Okay? It's driving away from that intersection. And what it says is that the policeman is 0.6 miles from the intersection. 0.6 miles, okay? And then it says the car is 0.8 miles from the intersection. The car that he sees speeding away is 0.8 miles from the intersection. And what it says is the policeman's radar shows the distance between them. Here's the hard part. This is the distance between them, okay, is increasing at a rate of 20 miles per hour. Well, the distance means this green piece is getting longer, and 20 miles per hour. But I don't know what kind of variable to assign that. I just know that it's a crucial piece of information, and it's related to that side of what looks like I'm doing something about triangles here. If the speed of the police car, so that's the police guy, so let me say the speed of the police car is 60 miles per hour, what is the speed of the car? Question mark, miles per hour. So now that I can see that I'm doing some sort of triangle, I'm guessing that I need the Pythagorean theorem because I probably want to know the length of the missing side. That green side, I do not know its length. Now, in my class, I do a leg squared plus leg squared equals hypotenuse squared. But in this case, it might be handy, say, for example, to just, why don't I assign this is x, say x equals that, and why don't I say that this is y, because this is, the x-axis and the y-axis on the coordinate plane. And then I can come in here and say that z is, what is z? Well, I recognize these numbers, 0.6 and 0.8. So I remember my Pythagorean triple 3, 4, and 5. And I remember that multiples of 3, 4, and 5 also work. So 6, 8, and 10. And there's a decimal. So that means it's probably move the decimal over one time. It's not 10. It's 1.0. But just for the sake of it, why don't I just write down the Pythagorean theorem? X squared plus y squared equals z squared. And I can solve for this using a calculator, okay? So I have my 0.6 being squared, and I have my 0.8 being squared, and I have my z being squared. Well, I want to solve for that. And it turns out I can. And how do I do that? Let me see. I want to go to my calculator and I want to type in, ready, 0.6 squared. And I want to do plus 0.8 squared. And that equals z squared. I got super excited here. I forgot to type in the solve. So there you go. I've typed in the solve. I forgot to put in that I was solving for z. And now, boom, my answer. Ooh, it says that it's either -1 or +1. Obviously, I'm dealing with distances here. So I'm going to say that it is +1. And I'm going to go ahead and label it right here. Z equals +1. Equals +1. So I know that now, and that's miles. So that's how far away they are at the moment. But remember that I know that things are changing. In fact, let me kind of detail for you exactly how things are changing. I'm going to zoom in on this. And I notice, by the way, that if this cop is moving in this direction, if he started here, then at some point he'll be here. You know what I mean? At some point, he'll be here. At some point, he'll be here. And my other guy, the bad guy, my perpetrator, he's going in this direction. So he's here right now, but in a moment, he'll be over here. You know what I'm saying? And so if I were to draw a triangle, what I'm noticing is that the lengths of all of the sides are constant. They're definitely changing. Okay? So this distance is getting smaller and smaller and smaller. So I know that if I want to introduce change over time, I need to take the derivative of this. And specifically, let me write it, I don't know, why not in hot pink? I'm going to apply a d dt to this, which means I'm going to get a dx dt, I'm going to get a dy dt, and I'm going to get a dz dt. And that's because all of the sides of this triangle are changing over time. This yellow version of the triangle is what happens after a while. There's even like an orange version of the triangle where that intersection, that cop is super close to it, but our perpetrator, he will have gone very far away. So there would be a very narrow triangle there. It doesn't look very good, so I'm going to erase it, but you get the idea. So now that I have figured out that the length of the distance between the cop and the intersection, it's getting smaller, I want to say that that's going to be negative. And so I have a dy dt that is actually negative. And for x, that actually, I believe, is the thing that I'm searching for. I want to know how far away this car gets. And so I will say this is my dx dt, and I'm searching for it. And the dz dt, it's definitely positive. It's definitely getting longer because if you pull this point, this guy, if you pull him away, then green will get stretched as well. So, I mean, I may not have drawn my yellow triangle exactly to the scale that it should be for the amount of time, but it's very likely not getting smaller because it says that dz dt is a positive number. It's getting bigger. Okay, that's something that we know. So now, have I taken care of all of the information that was given to me in this equation? Well, let's double check. 6.6 miles, I got that. And 60 miles per hour, I got that. And then 0.8, I got that. And the distance between them is increasing at a rate of 20. I got that. And what I'm looking for specifically is the speed of the car, and that should be a derivative because we remember that velocity is speed. So I think I've got everything. And I also did kind of get like this bonus piece of information, which was that z was 1, and I did that by using the solve function on my calculator so that I could right here go ahead and say that z equals 1. Oh, I should have said it in green. And by the way, you do want to double check and make sure that you write all that kind of stuff down. The fact that it's up here, a grader is supposed to look at your diagrams. And by the way, a point will be awarded for finding unknowns that you need in order to solve. So you will get a point for it, but just make your grader's life easier and write it somewhere neatly where you're actually performing work, and then they'll be able to see it. By the way, this piece that I highlighted in yellow, identifying what it is that needs to be found, what the question is asking for, and writing this notation can also be worth a point in a free response question. So literally just saying that I know that what I'm looking for is a dx dt can get you a point. All right, so then what else do I need to do? Well, in hot pink here, I did need to take the derivative. So applying a derivative to x squared, I should get a 2x and a dx dt. And applying the derivative to y squared, I should get a 2y dy dt. And when I take the derivative of z squared, I should get a 2z dz dt. I know everything except for which one? Which one do I not know? This one. Here. That's the only thing that I don't know. So I can plug in, for example, that I know that y is 0.6 and that dy is negative 60. And there is a 2 out in front of that. Although actually, if I look at this equation, do you see how there's a 2 here and there's a 2 here and there's a 2 here? Well, it looks like a 2 has been distributed to everything. I could actually multiply everything by a half, and the 2's just disappear. That makes it a little bit easier for me to solve. But you can leave the 2's in there, and you can still solve, and you'll still get the right answer, okay? So it's up to you how you go about it right now. In class, I noticed there was a little bit of confusion when I got rid of the 2's, so I'm not going to do it in the video, but here we go. 2x... X is 0.8, and I wanted to do that in purple, 0.8. And dx dt is the thing that I'm looking for, dx dt. And then plus 2y, and y was 0.6. And dy dt I know is a negative 60. And you can see it hanging out off the side there. That's my negative 60. And this equals 2z, and z was just a 1, and dz dt was a 20. And so now, again, I don't feel like doing this work by hand. I am just trying to understand the question and get the question correct. So I'm going to go ahead and put this into my solver, okay? So solve, and I want to do 2 times 0.8, and I want to do plus 2 times 0.6. Oh, that's right. There's supposed to be a variable here. Now notice dx dt is a command to my calculator. It says take the derivative of x with respect to t. I'm not asking the calculator to do that for me right now. I don't want it to find a calculation other than treating that dz dt as an unknown of an equation. So I'm just going to change it to another letter. How about p? Why not? That way I could just say, oh, well, you know what? I could actually do v, like for velocity. You know what I mean? How about v for velocity? And 2 times 0.6 times negative 60. And then this whole thing equals 2 times 1 times 20. And then I want to solve for v. And so I hit enter, and boom, what I got was 70. So here we go then. I can now write that dx dt equals 70. And please, please, please make sure that you put the miles per hour. You can actually do this 70 mph. Either one is allowed, but promise me that you do that. Because when you figured out the dx dt was the thing that you were looking for, that would be half of the point. The other half of the point would be awarded for finding the correct notation in units. Okay, now here's the part where you run into some difficulty. Okay, so identifying the unknowns is a point for you. And right here at this moment where I did that negative 60, if you do it incorrectly, you might accidentally get a positive 60, which is totally understandable, right? Because in the question, it just says 60. And by the way, I will mention that you probably can still get the right answer here as long as everything else works out. But the problem is that when they're looking for you to get the points for finding unknowns, if you put a positive instead of a negative, it doesn't work out. You don't get those points unless you 100% got the whole thing correct and your end answer is also correct. So here's something that you should plan to do in order to make sure that you get the maximum number of points. Ready? Write a sentence explaining the meaning of the answer. Right here. Write a sentence explaining the meaning of the answer. And I am going to do that because, like I said, the first time you do this, if you make a mistake on a plus sign or a minus sign, you can actually fix that mistake and still get a majority of points just with your sentence. Ready? The car... I would kind of like this to be bigger. The car is moving away from the intersection at the speed of 70 mph. Now, you might be wanting me to show you how to do it the other way, and I'll tell you, I don't actually know. I know it when I see it, that a kid gets the correct answer even though they set it up incorrectly, but I can't really like generate that on the fly. So we'll see as we go through these equations, if I end up naturally making that mistake and we end up getting there, then that's when you'll see that, okay? For number 2, I moved it over because I always need a little bit more room. It says a windlass is used to tow a boat to a dock. The rope is attached to the boat at a point 15 feet below the level of the windlass. If the windlass pulls in the rope at the rate of 30 feet per minute, at what rate is the boat approaching the dock when there is 25 feet of rope that's out? Write a sentence explaining the meaning of the answer. The hardest part about these word problems is actually just understanding the setup, okay? First of all, we don't know what a windlass is, but it turns out, I will mention, it's a winch. It's a rope coiler. And by the way, this particular rope coiler, it's so nice of him to give us this diagram, right? Step 1 is to write that diagram. And so the diagram has already been done for us. So the thing about this windlass is that it is on some kind of pole, all right? And I'm making it, be bold right here, that I know that it's on some kind of pole because the windlass isn't going to change positions, all right? This is actually right here. This is the dock. And I am supposed to be reeling this boat into the dock. And what you do is you throw out the end of the windlass. It's going to have a hook on it. The hook goes on to some sort of pin on the front of the boat right here. There's like a pin, and then you're supposed to be pulling the windlass or turning the winch on the windlass and bringing that boat in, which means there are two things that are changing here. Okay, so the length of the rope is going to be changing, and we're using Z for that, and the distance from the dock is going to be changing. That horizontal distance, by the way, down here, this is the water, right? And so the distance between the dock and the boat on the x-axis, that's a horizontal axis, that distance will also be changing. So I'm supposed to, as step 1, draw the diagram. Step 2, I'm going to be writing what is given and what is to be found using the variables, okay? So, I have a triangle here, and if you take a look at the geometry formulas on your paper, for right triangles, I have two different equations I could use. I could use this Pythagorean theorem, or I could use the area formula. Take a moment and think about the problem that we've been given and make a guess. Which formula do you think we are going to be using? Pythagorean theorem is for finding the lengths of sides, and the area formula obviously is for finding the area. Turns out, yes, absolutely, we should be using the Pythagorean theorem, because anything where you change the length of sides, you need to know how is that side length changing, and you also need to be able to use a formula that involves side lengths. So over here, I definitely want to be using some sort of x squared plus y squared equals z squared. And I do know that the length of the rope is changing, so there is going to be a dz dt. Now, in the AP exam, labeling what you know is actually worth points. So it'll tell you on the answer key, it'll say that if you identify known values, I can spell better than that, you will get a point for it. So I know that dz dt is how the rope length changes. And by the way, I've been given that information. It's a rate of 30 feet per minute. So I'm going to write down that number. And by the way, I do happen at this moment to notice that that number should be negative. How do I know? Well, the rope is getting shorter because I'm pulling it in. So I can throw that negative in there now. Now, can you do this problem correctly without having a negative there? Yes, you can. The key will be to write a sentence explaining the answer. So if you write that sentence, but you didn't notice the negative there, then when you write the sentence, if you write the sentence correctly, it'll be okay. And I'll show you that when we're at the end. So what else do I know? Well, I do know, let's see, I do know there's another number in here because we read this problem, and there's this. There's 25 feet of rope that is out. Well, shoot, doesn't that mean that I actually know that Z equals 25? Right here. If there is 25 feet of rope that is out, well, what's the relationship between the 25 and this negative 30? The rope is changing, so how many feet there are out will change every single minute. And so that means it's pulling stuff in relatively quickly, right? So it's changing by 30 feet per minute. So this boat is going to get reeled in less than a minute because there's 25 feet left out. So that's where we are, is right here. This distance is 25. And after a minute, it will have already been pulled up. right? Because it's capable of pulling in more than 25 feet a minute. It's capable of pulling in 30 feet per minute. So does that make sense? 25 feet is what Z is. Well, so that means that I know about one length and I know about another length, which means I can find that other length, right? The Pythagorean theorem, if I already know that Z is 25 and I already know that Y is 15. How did I know that that was Y? Because it's the vertical axis, right? This guy is definitely going to be Y. Then that means I can definitely find out what X is. And I want to do that. And I want to do it kind of right now. But hold on one more second. I did mention that Y is not going to be changing. That's the length of the pole. Let me talk about X. X definitely is changing. So we will find out what length X is when Z is 25. But we will also need to find dx dt, because I do not know how fast that is changing. And by the way, what rate is the boat approaching the dock? That is dx dt. Okay, that's the rate that the boat rate. It's the rate of the horizontal approach. Now, is that changing at 30 feet per minute? No, it's got to be changing at a slightly different number because it's on a different axis, okay? But it does have a relationship, and so I should go ahead and try to find X if you have X squared and Y is this 15 that is squared and Z is this 25 that is squared. Now, if you've been practicing with Pythagorean triples, I almost guarantee you that on the AP exam, they will use Pythagorean triples very often because they want this finding the X value piece to be very easy. They want it to be simple. So they say, if you know that the Pythagorean theorem, those Pythagorean triples exist, you would know then that the way this should work out, it's 15 squared plus 20 squared equals 25 squared. And you may have seen that in the freestyle that I mentioned that, which means that X is 20, right? So, but if you had to actually solve for it, it doesn't take that long. 15 squared, remember how I had you memorize that? It's because it's on the AP exam. 15 squared is 225. 25 squared might take you a minute, but you can definitely calculate it. It is 625. I'm going to minus 225 here. I'm going to minus 225 here. I'm going to say that X squared equals 400. And did I ask you to find the square root of 400 when you were in my Math 2 class? You know I made you memorize it. So here you go. X will equal the square root of 400 is 20. But you can just pull out a calculator and calculate it because this is definitely a calculator activated problem. So now that I know what X is, let's go ahead and find this dz dt, this dx dt, this thing that we're looking for, okay? Also, I want to double check. Right here, I forgot to write down the word, the dz dt. So I'm just wanting to highlight it because I'm going to need it in a minute. Now, the reason that I recorded this out of order was on number 3, you need to take the derivative of everything because that triangle is changing. But with this triangle, what you can see is that the height of the windlass is never going to change. It's on a pole, it's hooked up to some sort of, piece of wood, and it's never going to change its heights. So I don't ever want to take the derivative with respect to time on the y-axis because that's not changing. So what I'm starting out with is actually this equation right here. Ready? It's x squared plus y squared equals z squared. But I'm going to say that x squared plus y squared, since we know what y was 15, I'll throw that in here, and that is going to be equal to my z squared. The 15 never changes, so it's a constant. So when I take the derivative of it, it's going to disappear. Now mentally, at this point, hopefully you're ready, I'm going to apply a d dt, meaning that I'm going to take the derivative with respect to time. And when I take the derivative of x squared, I get a 2x, and I will get a dx dt. And that's the thing that I'm looking for, by the way. When I take the derivative of a constant, I get 0. Yay. And when I take the derivative of z squared, I will get a 2z dz dt. And let me say that again. The reason why I'm looking to get rid of y is because that length is not changing. When we look at example number 3, where we had the cop car that was moving, the cop car was getting closer to the origin, means that the length of that side, the y side, the vertical axis, it was changing. Here it is not changing. So I want to simplify my equation, which when we look at our steps again, real quick, we've looked at these a little bit. When we look at our steps again, if a quantity is constant, it must be represented with a number value. And this is the first time I'm doing it to you, so it feels weird. But trust me, it'll get more normal as we move on. Okay, so now I have 2x dx dt equals 2z dz dt. And by the way, I'm pretty sure that I can just solve for a dx dt by dividing by 2x. And so I have dx dt is equal to, well, the 2's cancel out, z over x times the dz dt. And so z was 25 and x was 20 and dz dt was negative 30. When I plug that into my calculator, what I end up getting here is a 75 over 2. And that is in feet per minute. And that would be my answer. So write a sentence explaining the meaning of the answer. What I would write, well, I'm going to type it because I'm a cheater. When the rope is 25 feet long, at that moment that the rope is 25 feet long, the boat's distance from the dock is decreasing at the rate of 75 over 2 feet per minute. Okay. Gravel's falling on a conical pile at the rate of 10 feet cubed per minute. Well, that's a rate, so some sort of derivative. At all times, the radius of the cone is twice the height of the cone. So, I mean, gravel's falling. I don't know how they managed to know such an amazing fact that the radius of the cone will be twice as big as the height of the cone. That's just the way that the gravel falls. It seems kind of amazing, but I'll write it down, you know. The radius is going to be twice the height. The yellow stuff, I'm not sure where to write it yet. Find the rate of change of the height of the pile when the radius of the pile is 6 feet. So I'm writing down pink stuff. The radius is going to be 6 feet at some moment. And it looks to me like I now have an equation I could solve for h pretty quickly. 2h equals 6, divide by 2, and I'll find out that h equals 3. So that's good to know. I've got a volume formula here because I'm trying to find the rate of change of the height of the pile, and I have a cone. I know everything's going into the shape of a cone. So in a volume formula, I've got a radius and I've got a height, and that gives me volume. It says gravel is falling on that conical pile at that rate. That was something I haven't written down yet. So it must be my dv dt. It's changing the volume. The gravel is changing the volume of my cone because it's falling onto that pile. So dv dt is equal to 10 feet cubed per minute. And I now know where to write it, so I'm going to highlight it. And then it says, write a sentence explaining the meaning of the answer. Okay, so I'm desperate to try and take the derivative of v because I know what I'm looking for is this rate of change of the height of the pile. So I'm going to say then that in orange, I'm looking for dh dt, I guess that's red, dh dt equals something, right? And that'll be, I believe, in feet per minute. And I'm writing it down so I don't forget. So the rate of change of the height of the pile, turns out I don't have anything any information that's going to tell me how the radius changes when the height changes. So if I can, I'm going to try and get rid of that h. And now this is the trick to these kinds of problems, is that I know that I need to do that. Why do I need to know? Why do I know? Well, because I've done these before. So let me go back for you and review these notes on steps, and let's see what I've done so far. The figure was drawn, okay, and variables for all unknowns were already given to me, v, r, and h. Write what is given and what can be found using my variables and my DDTs. So I've been writing what was given, and it says write an equation relating these variables. If a quantity is changing, it must be written with a variable letter. Boom, I did that. If a quantity is constant, it must be represented with a number. It turns out I don't really have anything that's constant here, right? The other example where we had that windlass and it was attached to a pole, that length was never changing. Here, you know, at one moment I had a very small cone, then I have a bigger cone, and eventually I'll have an even bigger cone. The volume, the radius, the height, they will always be changing. But here is something that I do definitely have. Ready? Look for secondary relationships between quantities to reduce the number of variables. I know that I can relate the radius to the height because I've already done that. Ready? This is step 3C, where I know that the radius is equal to 2 times the height. So I'm going to zoom in here and write down I'm going to write in my volume formula, and I'm going to do this. 1/3 pi r is squared h. I'm going to get rid of r by saying that it is twice the height. That's me plugging in my known value of what r is. I tried to highlight it, but it just didn't show up on the computer. Here we go. There we go. Okay? And by the way, when I simplify this out, I will get 1/3 pi, 2 being squared is a 4, and h being squared times h will be an h cubed. So eventually, I believe I will have a 4 times a 1/3, which is 4/3 pi h cubed. And that formula for volume, I can now apply my derivative to it. So I'm doing a d dt. I'm taking the derivative with respect to time. And I'm going to generate a dv dt. And I'm going to have a 4/3 pi. And h is cubed. When you take the derivative of that, you get 3h squared and a dh. Sorry, a dh dt. Okay, awesome. By the way, there's a 3 in the denominator and a 3 in the numerator, so those disappear. And when I simplify this just a little bit further, I get dv dt equals 4 pi h squared dh dt. Now I know all these pieces where I could say that dv dt is 10. And I know that there's a 4 and a pi, and the height, we had to solve for it. It's right here. I didn't give it a color. I'm going to give it a color now. H is 3. It's squared, and dh dt is the thing that I'm looking for, dh dt. And it's the only unknown that I have now. So I'll finish this off by saying that 10 equals 4 pi times 9 dh dt, and I can divide by that. So dividing by 4 pi times 9, well, 4 times 9 is 32, so I'm dividing by 32 pi, and I'm dividing by 32 pi, and that's something I can reduce. So dh dt is equal to 5/18 pi. 10 can be divided by 2, you get 5. 32 can be divided by 2, and you get, 36, my bad. 36 divided by 2 is 18, and so 5/18 pi is my answer, and I don't have to put this into a calculator, okay? You can leave it as an exact answer, but make sure you put that feet per minute down. And that's your answer, except don't forget, it said, please write a sentence. Up there somewhere it says, please write a sentence explaining the meaning of your answer. So here's our explanation, okay? When the radius is 6 feet. The height of the pile is increasing at a rate of, and I'll just move this down here so that they match. Ready? At a rate of boomity bomb, blippity blop. Oops. This is my answer. Ta-da!